Hello everyone, this is Group 13 and we have been tasked with a classical control system question, which is the given the open loop transfer function of a unity feedback control system as g of s being equal to k divided by s times 1 plus st, all into brackets. By what factor should the amplifier gain k be multiplied so that the damping ratio is increased from 3.0 to 0.9? So how do we go about this question? Well, we first lay down our equations, and our first equation, which is the equation of g of s, and our second equation, which is the unity feedback control system. Now we substitute equation 1 into equation 2 to get the corresponding equation. Now we have to first note that h of s is equal to 1 because the system is a unity feedback control system. Therefore, after further simplification, we result in a new equation, which is c of s divided by h of r of s, is equal to k divided by s plus s squared t plus k. Now, since our equation is in second order, we must make it to look like a second order equation by making s squared stand alone. To do this, multiply each term by 1 divided by t. Now, when we do that, we will result in the equation as shown below. Now, by comparison, you can see that k divided by t is equal to omega n squared, and s divided by t is equal to 2 times the damping ratio times omega n of s.
Our equation is a second order system. We want to rewrite it so that it matches the standard second order transfer function form. To do that, we divide every term in the denominator by t so that the coefficient of x squared becomes 1. This helps us compare it directly with the standard form used in control systems. After dividing by t, the transfer function then becomes what you see over here. We compare this with the standard second order transfer function, which is represented over here. From this comparison, we can already see that the constant term in the denominator corresponds to omega subscript n squared, and the coefficient of s corresponds to this. So this step prepares us to identify the natural frequency and the damping ratio by comparing the coefficients. Now, let's compare the characteristic equation of our system with the standard second order characteristic equation. Our equation is what we see over here. S squared plus 1 over 3s plus k over t is equal to 0. And the standard second order form is represented over here. By matching the two coefficients of both equations, we get two relationships. First, comparing the constant terms, omega n squared is equal to kt. Taking the square root gives the natural frequency of omega n is equal to the square root of k over t. Next, we compare the coefficient of s, which is 2, as you see over here. Then we substitute omega n is equal to the square root of k over t into the equation and solving for this. Now, from this, we are able to now get this relation. So from this comparison, we determine that the natural frequency is this, and the damping ratio is 1 divided by 2 times the square root of kt. Thank you.
This slide explains the concept of damping ratio, represented by the symbol zeta. The damping ratio tells us how quickly oscillations in a system die out after a disturbance. From the equation shown, zeta equals 1 divided by 2 times square root of kt. This means that the damping ratio depends on the system parameters k and t. If these parameters change, the damping behavior of the system also changes. In this example, we compare two damping ratios, 0.3 and 0.9. When zeta is equal to 0.3, the system is slightly damped, so it will oscillate more before settling. When zeta is equal to 0.9, the system is heavily damped, so it settles much faster with little or very little oscillation. A simple real-life example is car suspension system. If the damping ratio is low, the car keeps bouncing after hitting a bump. But if the damping ratio is higher, The car quickly stabilizes, giving a smoother ride.
Okay, so hello everyone. My name is Kelvin Senna, and I'll be continuing from where my colleague left off. So, from the earlier derivation, we had the damping ratio to be equal to 1 over 2 root K1T, where K1 is the gain and then T is the time constant, times 2 root K2T, where K2 is also a gain. So when you simplify it, that's when you cancel out the 2's and the T's and all the other stuff, you get the damping ratio to be equal to square root of K2 over square root of K1. And then when you rearrange and square both sides, you get K2 over K1 to be equal to the damping ratio 1 over damping ratio 2 all squared. This shows us how the system gain affects the damping behavior in and the stability in control system. Thank you.
Okay, so in continuation with where my colleague left off, we've been able to establish the mathematical link between the amplifier gain and that of the damping ratio, in which the damping ratio is inversely proportional to the square root of the amplifier gain. So with this, we'll be substituting the values of the damping ratio, in which we are increasing the state from unstable, that is 0.3, to a more stable state, that's 0.9. Thank you.
Okay, so now that we have established that the damping ratio is inversely proportional to the square root of the gain K, we need to calculate the exact factor for a specific change. Our goal is to increase the damping ratio from 0.3 to 0.9. So looking at the ratio of our target, our target damping to our initial damping, we have 0.3 divided by 0.9, which simplifies as 1 over 3. And since the relationship between the damping ratio and the gain involves a square root, specifically zeta 1 over zeta 2, which is equal to the square root of K2 over K1, we must square this ratio to isolate our gain values. By squaring 1 over 3, we find that the ratio of our new gain K2 to our old gain K1 is exactly 1 over 9. In practical terms, this tells us that to achieve a much higher damping ratio of 0.9, we must significantly reduce the amplifier gain. Therefore, the final result is that the initial constant K must be multiplied by a factor of 1/9. This adjustment ensures the system is built out, reducing oscillations as requested.
Hello, I'm Apia Gabriel Kofi, and I'll be continuing from where my group member ended. So my group member ended in the previous slide, where we realized or we obtained an expression when the ratios were simplified, and the expression obtained was K2 divided by K1 to be equal to 1 divided by 9. Yes, and in this slide we are going to find out the final result when we evaluate further. So moving forward, in order to determine the final result, we have to simplify it in a way such that we are going to obtain an expression for K2, because per the question you have to determine what factor the amplifier will be multiplied by. The amplifier gain will be multiplied by in order to increase the damping ratio from 0.3 to 0.9. And when the amplifier gain is multiplied by a factor, that means the initial gain will be multiplied by a factor to gain the final gain, or to obtain the final gain. Yes, and the final gain in this case is K2 and the initial gain is K1. So we are making the final gain
the subject, that is K2. We are making K2 the subject, and in doing so we are going to multiply both sides of the equation by K1. And when we do that, K1 cancels K1 at the left side of the equation, and then it multiplies the right side of the equation. So in that case, we are going to get K2 to be equal to 1 out of 9 multiplying K1. And that is the final result we obtain when we simplify or we evaluate further the ratios. My group member is going to take over from this point. Thank you.
So I'm going to go through the interpretation of the solution. So the question asks us that by what factor should the amplifier gain K be multiplied so that the damping ratio is increased from 0.3 to 0.9? And we have our solution to be K2 is equal to 1 out of 9 K1. And it says that this means that the new constant is 1/9 of the initial constant. It means that K2 is always 9 times smaller than K1. Hence, the initial constant must be multiplied by a factor of 1 out of 9. So let's say, for example, we have K1 to be equal to 90. So we multiply 90 by 1 out of 9 and we'll get 10. So K to be equal to 10. So the whole interpretation means that K2 is always smaller than K1. Thank you.